The universe is vast beyond comprehension. Our galaxy alone contains between 200 and 400 billion stars. Most of those stars have planets. Many of those planets orbit in the habitable zone where liquid water can exist. And the Milky Way is just one of hundreds of billions of galaxies in the observable universe. The numbers suggest that intelligent, technological life should be everywhere. Civilizations building radio telescopes, launching spacecraft, spreading across their star systems. We should see evidence of them, signals, structures, something. And yet we found nothing. No radio transmissions from distant worlds. No megastructures harvesting stellar energy. No probes visiting our solar system. No evidence whatsoever that we're not alone. This is the Fermi Paradox, named after physicist Enrico Fermi, who supposedly asked during a casual lunch conversation in 1950, "Where is everybody?" It's a simple question with profound implications. If life is common, if intelligence evolves naturally, if technological civilizations are a predictable outcome of cosmic evolution, then why haven't we encountered any? Why is the universe so quiet? Why are we drowning in silence? The paradox isn't just about absence of evidence. It's about the staggering improbability of that absence given what we know about the universe. Every solution to the paradox is unsettling in its own way. Maybe intelligent life is extraordinarily rare, and we're alone in a vast, empty cosmos. Maybe life is common, but something destroys it before it can spread, and we're next. Maybe civilizations hide deliberately, fearing contact. Maybe they exist, but have transcended physical reality into forms we can't detect. Maybe they're all dead, wiped out by disasters we haven't encountered yet. Or maybe, just maybe, we're among the first. The early arrivals in a universe that will one day teem with life, but hasn't yet. Every answer raises new questions. Every solution is either lonely, terrifying, or both. This is the story of the Fermi Paradox. Why the universe should be full of aliens. Why we haven't found any. And what that silence might mean for the future of intelligent life in the cosmos. By the end, you'll understand why some scientists look at the night sky with wonder, and others with dread. Welcome to the Great Silence. To understand why the Fermi Paradox is a paradox, you need to understand the scale of possibilities. In 1961, astronomer Frank Drake formulated an equation to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It's called the Drake equation, and it looks like this: N equals R asterisk times FP times NE times FL times FI times FC times L, where N is the number of civilizations we might detect. R asterisk is the rate of star formation in our galaxy. FP is the fraction of stars that have planets. NE is the average number of planets that could support life per star with planets. FL is the fraction of those planets where life actually develops. Fi is the fraction of life-bearing planets where intelligent life evolves. FEC is the fraction of intelligent species that develop technology detectable across space. L is the length of time such civilizations release detectable signals. Let's plug in conservative numbers estimates that assume life and intelligence are rare, not common. Stars form in the Milky Way at a rate of about 1 to 3 per year. Let's say 1.5. We now know from missions like Kepler that nearly every star has planets, let's say 100% to be generous, but even 50% works. Of those planetary systems, perhaps one planet per system is in the habitable zone where liquid water can exist. So far, 1.5 stars year times one planet inhabitable. Zone equals 1.5 potentially habitable planets forming per year in our galaxy. Now the uncertainties begin. What fraction of habitable planets develop life? We have no idea. Let's be pessimistic and say 1%. What fraction of life-bearing planets develop intelligent life? Again, we don't know. Let's say 1%. What fraction of intelligent species develop detectable technology? Maybe 1%. Even with these conservative estimates, 1% at every uncertain step you get. 1.5 times 0.01 times 0.01 times 0.01 equals 0.00000015. Technological civilizations arising per year. That sounds tiny, but the Milky Way is 13 billion years old. Even if technological civilizations only last 10,000 years before going extinct, a pessimistic estimate, and even with our conservative numbers, there should have been thousands of civilizations in our galaxy's history. And if any of them expanded beyond their home star, something humans are already contemplating with Mars colonization and interstellar probes, they would have had millions or billions of years to spread across the galaxy. At just 1% the speed of light, a civilization could colonize the entire Milky Way in about 10 million years. That's nothing on cosmic timescales. A rounding error. If even one civilization in our galaxy's 13 billion year history developed interstellar travel and decided to expand, they should be everywhere by now. We should see their presence. Dyson spheres harvesting stars, terraformed planets, von Neumann probes replicating across star systems, megastructures, something. And that's just our galaxy. There are hundreds of billions of galaxies in the observable universe, trillions upon trillions of planets. The odds that intelligent life arose exactly once here on Earth and nowhere else seem absurdly small. Yet here we are, alone, listening to the cosmos with radio telescopes, hearing nothing but cosmic background noise. The numbers say aliens should exist. The silence says they don't. Something is wrong, either with the numbers, or with our assumptions, or with reality itself. Maybe we just haven't looked hard enough. Maybe the aliens are out there, broadcasting, and we simply haven't tuned to the right frequency or pointed our telescopes in the right direction. This is a fair objection. Space is big, really big, and we've only been seriously searching for extraterrestrial intelligence for about 60 years, a cosmic eye blink. The search for extraterrestrial intelligence, or SETI, began in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for artificial signals. He heard nothing. Since then, SETI has expanded dramatically. Projects like the Allen Telescope Array, Breakthrough Listen, and others have scanned millions of star systems across multiple frequencies. They've listened for narrowband signals that wouldn't occur naturally, for patterns in radio noise, for anything that might indicate an artificial origin. They've found nothing. Well, almost nothing. In 1977, the Big Ear Radio Telescope at Ohio State University detected a strong signal from the direction of Sagittarius. It was so unusual that astronomer Jerry Emmon wrote "wow" in the margin of the printout. The "wow" signal lasted 72 seconds and was never detected again, despite repeated attempts to find it. Was it aliens? Probably not. Most likely, it was interference from a satellite or comet, though we'll never know for sure. But it's the closest thing we've ever found to a potential extraterrestrial signal. Everything else has been silence. To be fair, our searches have been limited. We've primarily looked for radio signals because that's what we know how to detect and what we assume other civilizations might use. But maybe advanced civilizations use communication methods we haven't imagined: quantum entanglement, neutrino beams, gravitational wave modulation. Maybe they don't broadcast at all. We've also only searched a tiny fraction of the sky at a tiny fraction of possible frequencies for a tiny fraction of cosmic history. The observable universe contains about y stars. We've carefully examined perhaps a few million. That's like dipping a cup into the ocean and concluding there are no fish because you didn't catch any. But here's the thing, we're not just looking for deliberate signals. We're also looking for technosignatures, evidence of technology that isn't meant to communicate. When you look at Earth from space, you can see artificial lights on the night side. Radio and television broadcasts leak into space. There's atmospheric pollution from industry. Our civilization is detectable to anyone with telescopes pointed our way, even if we're not trying to send messages. If there were a civilization like ours around any star within 100 light years, we'd probably notice. Not with certainty, but we'd see something. And we've seen nothing. Maybe advanced civilizations don't produce detectable waste radiation. Maybe they're too efficient, too quiet, too careful. Maybe. Or maybe there's nobody there to detect. The silence is deafening. And the longer it continues, the stranger it becomes. One of the most discussed and most unsettling solutions to the Fermi Paradox is the Great Filter hypothesis. The idea is simple but chilling. Somewhere between the formation of a planet and the creation of a galaxy-spanning civilization, there's a filter. A barrier so difficult to pass that almost no one makes it through. Something that prevents the transition from non-life to life, or from simple life to complex life, or from complex life to intelligence, or from intelligence to technological civilization, or from technological civilization to interstellar expansion. The Great Filter could be behind us. Maybe the origin of life is incredibly rare. Maybe the jump from single-celled to multicellular life almost never happens. Maybe intelligence is a cosmic fluke, and Earth won the lottery. If the filter is behind us, that's good news. It means we've already passed the hard part. It means the path ahead is relatively clear, and if we don't destroy ourselves, we might one day spread across the stars and find a galaxy empty and waiting for us to fill it. But if the filter is ahead of us, that's terrifying. Maybe every technological civilization destroys itself before achieving interstellar travel. Maybe nuclear war is inevitable. Maybe climate collapse is unavoidable. Maybe artificial intelligence goes wrong. Maybe there's some technology we haven't discovered yet that's so dangerous it kills everyone who invents it. If the filter is ahead, then the silence makes perfect sense. There are no aliens because they all died. They reached our level radio telescopes, space probes, nuclear weapons, and then something happened. War. environmental catastrophe, runaway technology, extinction, and we're next. The Great Filter hypothesis suggests that the universe might be full of dead civilizations, ruins on airless worlds, cities overgrown by forests, radioactive wastelands, the remnants of species that got close but didn't make it. Here's the worst part. Every time we don't find aliens, the filter being ahead of us becomes more likely. If we found microbial life on Mars, that would be bad news for the Great Filter hypothesis. It would mean the origin of life isn't the filter life is common. If we found ruins of a dead civilization on an exoplanet, that would be even worse. It would mean civilizations arise, but something kills them. The more common we find life and intelligence to be, the more likely it is that there's a universal disaster waiting for technological species. And the fact that we see no evidence of any civilization anywhere suggests that if the filter exists, it's extremely effective. Some scientists have argued that perhaps the filter is nuclear weapons. Every species that develops nuclear technology eventually uses it in a global war and wipes itself out. Or maybe it's every species creates artificial superintelligence, and that intelligence either destroys them or transcends them in ways that make them undetectable. Or maybe it's something we haven't even thought of yet. Maybe there's a technology that seems beneficial, that every civilization inevitably pursues, and it destroys them before they realize the danger. Climate change could be part of the filter. If every industrial civilization inevitably warms its planet past the point of habitability, that would explain the silence. We might be right in the middle of the filter right now, racing against time to transition to sustainable energy before it's too late. The Great Filter is a race, and the question is, are we running toward the finish line or toward the cliff? Maybe there's no Great Filter. Maybe life is just incredibly, unimaginably rare. Maybe Earth is special in ways we don't fully appreciate, and the combination of factors that led to us is so specific that it almost never happens elsewhere. This is the Rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee in their 2000 book. The argument goes like this. Yes, there are billions of planets, but how many are actually suitable for complex life? You need a star that's not too massive, or it burns out too quickly for life to evolve, and not too small, or its habitable zone is so close that planets become tidally locked. You need a planet at the right distance, the habitable zone, where water can be liquid. But that's just the beginning. You need a large moon to stabilize the planet's axial tilt, preventing wild climate swings. Earth's moon does this for us. Without it, our axis would wobble chaotically, making the climate too unstable for complex life. You need plate tectonics to recycle carbon and regulate the atmosphere over geological time. Most rocky planets probably don't have plate tectonics. They're either too small, like Mars, where tectonics died early, or too hot, like Venus, where the entire crust may periodically melt and reset. You need a magnetic field to protect the atmosphere from being stripped away by solar wind. Mars lost its magnetic field and most of its atmosphere billions of years ago. You need a Jupiter-sized planet in the outer system to act as a shield, deflecting comets and asteroids that would otherwise bombard the inner planets constantly. Without Jupiter, Earth would be hit by extinction-level impacts far more frequently. You need to be in the galactic habitable zone, not too close to the galactic center, where radiation and supernova are common, not too far out where heavy elements are scarce. You need the right type of galaxy, a spiral with moderate star formation, not an elliptical with old stars and no new planets, not an irregular with chaotic star-forming regions. And you need time. Complex life on Earth took about 4 billion years to evolve. Simple life appeared relatively quickly, but the jump to multicellular organisms took billions of years. Intelligence took even longer. Every one of these factors is necessary, and every one narrows the possibilities dramatically. When you stack all these requirements together, maybe Earth-like planets with Earth-like conditions are extraordinarily rare. Maybe they occur once per galaxy, or once per cluster of galaxies. Maybe we're one of a handful of places in the observable universe where everything aligned perfectly. If this is true, the Fermi Paradox isn't a paradox at all. We haven't found aliens because there are no aliens to find. We're alone not because something destroys civilizations, but because civilizations almost never arise in the first place. The universe is full of sterile rocks orbiting dead stars. Life is a cosmic accident that happened here and almost nowhere else. This is a lonely solution, but it's not terrifying. It means we're not facing some inevitable filter. It means we're special, precious, the only minds in the cosmos capable of understanding the cosmos. It also means we have a responsibility. If we're the only ones and we destroy ourselves, we're not just ending human civilization. We're extinguishing the only light of consciousness in an otherwise dark and empty universe. Maybe aliens exist. Maybe they're common. Maybe some are even watching us right now. But they're staying hidden, deliberately. This category of solutions suggests that the silence isn't because aliens don't exist, but because they're choosing not to make contact. And there are several reasons why they might do this. The zoo hypothesis proposes that Earth is essentially a nature preserve. Advanced civilizations know we're here, but they've agreed not to interfere. They're observing us the way we observe animals in the wild, from a distance, with minimal disruption. Maybe there's a galactic protocol. Don't contact primitive civilizations until they reach a certain technological threshold. Don't contaminate their cultural development. Let them evolve naturally. This is similar to Star Trek's Prime Directive, which forbids interfering with less advanced civilizations. If most or all spacefaring species follow something like this, we wouldn't detect them until they decided we were ready. It's a comforting idea. It means we're not alone, just uncontacted, protected, given space to develop on our own. The dark forest theory, proposed by science fiction author Liu Cixin, is far more sinister. It suggests that the universe is like a dark forest at night. Every civilization is a hunter with a gun, creeping through the trees. They know other hunters exist, but they don't know their intentions. In this scenario, revealing your position is suicidal. If you broadcast your existence, you're gambling that whoever hears you is friendly. But if they're not, if they see you as a potential threat or as resources to be harvested, they might destroy you preemptively. So everyone stays silent. Everyone hides. The moment you detect another civilization, you face a terrible choice. Destroy them before they destroy you, or risk that they'll do the same. The silence, in this view, is not emptiness, but predation. It's a universe full of civilizations holding their breath, afraid to make a sound. This would explain why SETI has found nothing. It would explain why, if we ever do detect an alien signal, our first instinct should not be to respond, but to shut up and hide. It also suggests that humanity's broadcasts the radio and TV signals we've been leaking into space for a century might have been a catastrophic mistake. We've announced our presence to a potentially hostile galaxy. And if the dark force theory is right, we might already be marked for extermination with a relativistic kill vehicle on its way to sterilize our planet. There's another possibility. Civilizations are common, but they're not interested in us. Maybe post-biological civilizations have transcended physical reality, uploading themselves into computational substrates. Maybe they exist in dimensions or states of being we can't perceive. Maybe they're focused inward, building Dyson spheres around their stars not for expansion, but for energy to run vast virtual realities where they live as digital gods. If advanced civilizations don't explore or colonize, if they're content to stay home and build megastructures for computation, we'd see evidence of them, Dyson spheres blocking starlight, but they wouldn't contact us because we're not relevant to their interests. We'd be like ants trying to get the attention of humans. We're down here building anthills, and they're building the internet. Why would they care? Maybe we're not late to a galaxy that should be filled with ancient civilizations. Maybe we're early. The universe is 13.8 billion years old. That sounds ancient, but in cosmic terms, it's still young. The universe could exist for trillions of years long enough for stars to burn out, for galaxies to collide and merge, for the last red dwarfs to fade into darkness. We're living in the first fraction of cosmic time. Early in the universe's history, conditions weren't favorable for life as we know it. The first stars contained almost no heavy elements, just hydrogen and helium from the Big Bang. Planets like Earth, made of carbon, oxygen, silicon, iron, couldn't form yet. Those elements had to be created in stellar furnaces and scattered by supernova. It took billions of years for the universe to produce enough heavy elements to make rocky planets common. The oldest rocky planets probably formed 10 billion years ago, but most formed more recently. If Earth-like planets are a relatively recent phenomenon, and if complex life takes billions of years to evolve, then maybe we're among the first. Maybe in a billion years the galaxy will be full of civilizations, but right now there are only a handful, separated by such vast distances that we'll never encounter each other. This is the early arrival hypothesis. It's optimistic in a way. It means the great filter isn't real, the galaxy isn't hostile, and we have a chance to spread and flourish. The universe is empty, not because something destroys everyone, but because we got here first. But there's a darker version of this idea. Maybe civilizations have existed, but they're all dead now. Maybe intelligent life arises, reaches our level of technology, lasts 10,000 or 100,000 years, and then goes extinct. Not because of a filter, necessarily, but just because civilizations are fragile. They collapse, they stagnate. They lose the drive to expand. Human civilization is only about 10,000 years old. We've had radio for 130 years, spaceflight for 65 years, nuclear weapons for 79 years. We're infants on the cosmic stage. Maybe most civilizations don't last much longer than this. Maybe they burn bright and fade fast. If the typical technological civilization lasts 50,000 years, and if civilizations arise randomly across billions of years of galactic history, the chances that two civilizations exist at the same time and close enough to detect each other are tiny. You could have a galaxy that has hosted thousands of civilizations over its history, but at any given moment, most of it is empty because those civilizations have already come and gone. We might be living in the ruins of a once bustling galaxy, surrounded by the ghosts of dead empires we'll never know existed. Or maybe civilizations don't die, they transcend. They upload themselves into digital substrates. They leave the physical universe behind, existing in higher dimensions or as post-biological entities we can't detect. From our perspective, they vanish. But from their perspective, they've just moved to a better neighborhood. If this is common, then the universe is full of advanced civilizations. We just can't see them because they're no longer operating on our level of reality. Every solution to the Fermi Paradox carries implications, and many of them are dark. If the great filter is ahead of us, we're living in the most dangerous period of human history. Every day we survive is another day we've defied the odds. Every technological advancement could be the one that kills us. Nuclear war, engineered pandemics, runaway AI, nanotechnology gray goo, climate collapse. Something we haven't imagined yet. The silence of the cosmos might be a warning written in the absence of signals. This is as far as anyone gets. If the rare Earth hypothesis is true, we're alone. Truly cosmically alone. The only intelligence in a galaxy of 400 billion stars. Possibly the only intelligence in the observable universe. That makes our extinction not just a human tragedy, but a cosmic one. If we fail, the universe returns to darkness. No one will remember us. No one will mourn us. The last light goes out. If the dark forest is real, we're prey. Our broadcasts over the past century have announced our location to anyone listening. And if there are predators out there, they now know where to find us. The galaxy isn't empty, it's hostile, and we've made ourselves a target. If civilizations are common but don't expand, if they stay home and turn inward, that might be the future awaiting us. Not exploration and expansion across the stars, but retreat into virtual worlds. Humanity building Dyson spheres not to fuel starships, but to run simulations, uploading ourselves into digital paradises while the physical universe goes unexplored. Is that success? Or is it a kind of death? And if civilizations rise and fall on timescales too brief for contact, if the galaxy is full of ruins, that suggests a fragility to intelligence we might share. Civilizations don't last. They collapse, empires fall, species go extinct. The question isn't if, it's when. There's also a possibility no one likes to talk about. Maybe intelligence isn't adaptive in the long run. Evolution doesn't care about space exploration or philosophy or art. It cares about reproduction. And on most worlds, the traits that lead to intelligence, curiosity, innovation, abstract thinking, might not actually increase reproductive success. Maybe intelligence is a dead end. Maybe it arises, gives a temporary advantage, then selects itself out of existence as populations optimize for simpler, more efficient survival strategies. Or maybe intelligence leads inevitably to self-destruction. Maybe the same traits that let you build radio telescopes also let you build nuclear weapons, and the latter always wins. The Fermi Paradox forces us to confront uncomfortable truths. We're either alone, hunted, doomed, or irrelevant. There's no solution that isn't, in some way, unsettling. But here's the thing. We don't know which it is. The paradox remains unresolved. And in that uncertainty lies both danger and hope. On a clear night, far from city lights, you can see thousands of stars. Each one is a sun, many with planets. Some of those planets are rocky. Some orbit in habitable zones. Some might have liquid water, stable climates, all the ingredients for life. And as far as we know, none of them have anyone looking back at you. The Fermi Paradox is one of the most profound questions humanity has ever asked. It sits at the intersection of cosmology, biology, philosophy, and existentialism. Where is everybody? Why are we alone? What does the silence mean? We don't have an answer. Not yet. Maybe not ever. Every explanation has its advocates. The great filter, rare earth, the zoo hypothesis, dark forest, early arrival, transcendence. Each fits some of the evidence. None fits all of it. Maybe the truth is some combination. Maybe life is rarer than we think, and civilizations face filters, and some hide deliberately. Maybe the answer is complex, multi-layered, different in different parts of the universe. Or maybe the answer is simple, and we just haven't thought of it yet. But here's what we do know. We're here, against enormous odds on a planet with the right star, the right orbit, the right moon, the right magnetic field, the right geology. We're here. Life emerged. It complexified. It evolved intelligence. It built civilizations. It created telescopes and spacecraft and began asking where everyone else is. That alone is extraordinary. Whether we're the only ones or one of billions, the fact that matter arranged itself into configurations capable of contemplating the cosmos is miraculous. The Fermi Paradox might be telling us we're alone, or it might be telling us we're early, or it might be telling us we're in danger. We can't know yet, but we can choose how we respond. If we're alone, that makes us precious, irreplaceable, the custodians of the only consciousness in the cosmos. We have a responsibility not to waste that, not to destroy ourselves, to survive, to spread, to become the first light in a dark galaxy. If we're not alone but hidden from, maybe one day we'll reach the threshold where contact is permitted. Maybe we'll join a galactic community, learn we were never alone, just quarantined until we grew up. If we're in a dark forest, we need to be careful. We need to think before we shout into the void. We need to understand that the universe might be more dangerous than we've imagined. And if the great filter is ahead, we need to recognize it and navigate it. We need to solve the problems that might destroy us: climate change, nuclear weapons, artificial intelligence, whatever challenges await. Because if we don't, we'll join the silence. We'll become another dead world, another failed experiment, another species that got close but didn't make it. The Fermi Paradox doesn't have to be solved to teach us something. The silence itself is information. It tells us that whatever the truth is, we should proceed with caution, with humility, with the understanding that we might be more fragile and more significant than we ever imagined. For now, we listen, we search, we build better telescopes, We scan more stars. We refine our models and wait for data. And we stand in the silence, one species on one planet, looking out at a quiet universe, wondering if anyone is looking back. The answer to the Fermi Paradox might be the most important thing we ever discover, or the most important thing we never do. Either way, the question changes everything.